In this video, we're going to define the trig functions. Now, there is some prerequisite knowledge that you must know. So in a previous video, we discussed four main ideas, which were coterminal angles, central angles, standard position, and radian measure. So if you still are needing to practice those topics, please go review that previous video. And even before I can define the trig functions in this video, I have a couple more vocabulary terms to go over, to introduce to you. The first one is a quadrantal angle. A quadrantal angle is simply an angle in standard position, and the terminal side lies on one of the quadrants. So it's on the x-axis or it's on the y-axis. A quadrantal angle is an angle in standard position with its terminal side on the x or y axis. So can you think of any example angles where their terminal sides lie on one of the axes? Probably the most common would be something like 90 degrees. 90 degrees points straight up. It lies on that y-axis. We call 90 degrees a quadrantal angle. Something like pi. So if I just switch over to radians, 180 degrees, or 1 pi, that's sitting on the x-axis, and so therefore a quadrantal angle. Another example, how about negative 3 pi halves? So I'm going to count this out. Negative 1 pi halves, negative 2 pi halves, negative 3 pi halves. Negative 3 pi halves is coterminal to 90 degrees. They share that terminal side pointing straight up, and we call these quadrantal angles. All right. Now, this begs to, we're now curious, what is a non-quadrantal angle? Well, a non-quadrantal angle is simply an angle that does lie in a quadrant. And non-quadrantal angles have something that we're going to need today called a reference angle. Let's write down the definition real quick. If theta is a non-quadrantal angle, in standard position, then the reference angle of that angle is going to be defined as the angle that goes from the terminal side to the x-axis, and it's the positive or the shorter angle. Let me just finish writing this down. And the reference angle of theta is the positive acute angle formed by the terminal side and the x-axis. All right, that's a lot of words, but let me draw a picture to help explain this reference angle idea. So let's just do a quick little example of finding one. Let's find the reference angle for 120 degrees. All right, first things first, I'm going to get a visual of 120 degrees. I'm going to draw this in standard position. So I have my Cartesian plane. I know if I start on the initial side, which is the positive x-axis, and just go in a counterclockwise rotation, that's creating a positive angle. I'm going to go 90 plus another 30, which is about a third of a quadrant, or is a third of a quadrant. And this red angle is 120 degrees, and yes, I would call this a non-quadrantal angle. It does not lie on one of the axes. Because it does not lie on one of the axes, it has a reference angle. The reference angle is formed by the terminal side and the x-axis. Now you may think to yourself, well, 120 is an angle formed by the terminal side and the x-axis. But 120 is obtuse. It is bigger than 90 degrees. So I'm looking for the acute one. So I'm going to draw this angle. This is the acute little angle formed by the terminal side and the x-axis. And I am going in a positive direction, so there's no debate here. But even if you're kind of going like clockwise, so you may think you're going in a negative direction, we will always talk about these reference angles as being positive. So this is a positive 60 degrees. 120 degrees has a reference angle of 60 degrees. Let's do another one. Let's find the reference angle for 210 degrees. In fact, pause the video and see if you come up with the same reference angle as I do. (210 degrees lies in quadrant 3, and it is 30 degrees away from the x-axis. So I say 210 degrees has a reference angle of 30 degrees. Once we define the trig functions, we'll see that these large angles, the bigger and bigger they get, we're going to be using reference angles when we're actually evaluating these trig functions. All right, let's see if I can do, let's just do one more. Oops. I'll do another big angle. How about something like 405 degrees? Again, maybe pause the video, see if you can get the reference angle. I am going to start by drawing 405 degrees in standard position. Now this is bigger than a full revolution, so I may go off and find a coterminal angle as well, just so I can start to talk about it. But I've got my Cartesian plane. I know a full circle makes 360 degrees. Which is a 45 degrees left over. So I make my full 360 plus another, I shouldn't have put that arrow there, another 45 degrees. I draw my terminal ray. getting kind of messy, but it's a full revolution and 45 degrees. That is a big angle of 405 degrees. The reference angle is formed by the terminal side and the x-axis, and it's always the smaller of the two. A lot of students, when I walk around in the classroom, they will try to draw the angle to the y-axis, but no. The definition clearly states the x-axis, and we're talking about the acute angle, and we're going to think of it as a positive. So this green angle here is 45 degrees. 405 degrees has a reference angle of 45 degrees. Now that happens to also be its coterminal angle, but that's not always going to be the case. Like in the previous example, 120 and 60, those are not coterminal angles. 60 degrees lies in quadrant 1. 120 has a reference angle of 60. 405 has a reference angle of 45 degrees. Which just happens to be coterminal to 45. Two different things though. All right, those are reference angles. Now I think I'm finally ready to introduce the trig functions. Now, trig functions are a bit peculiar, especially the way we think of their inputs and outputs. So if you just came from a college algebra course, that course usually focuses around functions, but you're dealing with functions that normally the inputs are the x-axis, the outputs are the y-axis. So something like the square root functions, a rational function, you're plugging in real numbers from the x-axis, and you're getting out y values from the real numbers as well. And that's great. But functions are not, they're just input and output. It doesn't have to be real numbers. You put in objects. If the function spits out an object, one distinct one, then we call that a function. So the trig functions, they're interesting. We think of their inputs. We usually think of them as the interior angles of a right triangle. So if I asked you what would be maybe a common input of a trig function, you might say something like 45 degrees. 45 degrees is an angle you can find in a right triangle, like 30 degrees or 72 degrees. I just can't go bigger than 90. Now, we will, if we do, I'm getting ahead of myself, but if we do come across large angles, what we're going to do is refer to their reference angle, and their reference angle will always be acute. So it does kind of fit that definition of we're thinking of them as the interior angles of a right triangle. All right. Now the outputs, we usually think of the outputs of a trig function as a ratio of side lengths of that right triangle. All right, I always like to show like images just to help me with my definitions. So here is a right triangle I'll go ahead and label the sides. Let's call this A, B, and the hypotenuse C. And let's give us an interior angle, and I'll call it something like theta. So theta is kind of what we think of as the input. The input of these trig functions are the interior angles of a right triangle. So there's this theta, this red one, and then this other high one that would be an interior angle. The outputs are a ratio of side lengths. So what would be a good output? Remember, ratio is just another word for maybe fraction. So how about B to A, or B over A? And if B over A can be an output, its reciprocal A over B, that could be an output. And I'll just kind of continue pairing up letters here. B over C, C over B. And how many of these ratios will there be in total? 1, 2, 3, 4. Looks like I could do C and A. So there are 6 possible ratios, these outputs, and those are the 6 trigonometric functions. I'm going to write down their names first before I define them real quick. One of them is called sine. When we denote it or write it down, we typically just say S-I-N, but we pronounce that sine. There's a cosine, which is cos, or C-O-S for short. There's a tangent, tan for short. Now these 3 trig functions have reciprocal functions. So notice the B over A and A over B, they are reciprocals of each other. Sine has a reciprocal function called cosecant, which is CSC for short. I mean, don't call these reciprocals. Cosine has a reciprocal function called secant, or SEC for short. And tangent has a reciprocal function called cotangent. Or COT, or cot for short. Now, these are the reciprocal relationships. Sine has a cosecant reciprocal, cosine has a secant reciprocal, and tangent and cotangent are reciprocals. In a future video, we will talk about a co-relationship, which may be confusing at first, because it kind of seems like sine should go with cosine, and secant should go with cosecant, but that's a different relationship we'll talk about later. So right now, in this first introduction, just want you to be familiar with these 6 functions and know that these relationships are reciprocal relationships. All right. I think I'm finally ready to define one of these functions. To do so, I'm going to draw a circle in standard position. That is, I'm going to pick up a circle and put it on the Cartesian plane where the center of the circle happens to be the origin of the Cartesian plane. I think I'll use a straight edge just for fun. I think I'll bust out a compass to help me draw a circle. Get a little bit bigger. How about that? That's good. And then I'm going to pick a point on the circle and give it a label. I think for this first example, I'll just choose quadrant 1 where everything's nice and positive. Everyone's comfortable there. So I'm just going to choose a point on this circle, and I'm going to label it xy. This coordinate has some x value. It goes over to the right, some x value, and then it goes up some y value. And if I did quadrant 2, well, that x would be negative and the y would be positive, but it's the same idea. I'm just choosing a point out in space on the circle, and then I'm going to draw a ray through that point. Of course, the ray is coming from the origin of the circle. This is giving me the vertex of an angle. Remember let me make that dot a little bigger. Remember the initial side, or there's this ray pointing due east. Then I'm going to draw that reference angle. So this terminal side has something called a reference angle. And we just discussed that it's always formed by the terminal side and then the x-axis. And it's not the obtuse one, it's going to be this acute one. So drawing from my terminal side to the x-axis, I have this reference angle. I'll go ahead and call it theta. Now, theta is the input for these trig functions. That interior angle is the input, or what we think of as the input of these trig functions. But I really need a right triangle. So what I'm going to do is I'm going to take this point, xy, and I'm going to drop a perpendicular. That is, from that point, I'm going to draw a straight line down, creating a right angle. Now I have a right triangle where this reference angle is the interior angle of that right triangle. Well, the output are the side lengths, different ratios of the side lengths. So I need to label these different side lengths. But I think I already have good labels. The distance from the origin out to here, so the base of this triangle, well, isn't that just this x value? The height of this triangle from 0 up to this point, isn't that just the y value? And then a good name for this line segment, you may want to call it the hypotenuse or something like z, but I think there's even something better. Because we're dealing with a circle, this is just the radius of that circle. All right, here we go. Sine of theta is defined as the ratio y over r. Definition. Sine, the trig function. We're going to input some interior angle. It's going to spit out some ratio of side lengths of that triangle. And the ratio is going to be the y value over the radius. We said earlier, sine has a reciprocal function called cosecant. Cosecant of theta uses those same variables, but it's the reciprocal. It's equal to the radius over the y value. Cosine of an interior angle, of the right triangle, is defined as the horizontal distance, or the x, over the radius. Cosine has a reciprocal function called secant, r over x. Tangent. Tangent is defined as y over x. Its reciprocal is the last ratio we could write, because remember there's only 6 of these ratios. Cotangent of theta is x over y. All right, these things are the definitions of the 6 trigonometric functions. And I have them written off to the side over here, up above me. This is the main goal for today's video, or this video. I'm going to now show some examples of finding these values, and hopefully with repetition, we can not only learn how to use these definitions, but get them embedded in our memory. So box those. I'm going to leave them right here as I move on. Let's do an example of a problem you may see in the homework. I want to find values of the 6 trig functions of theta and the information I'm going to give you is just a point flying out in space. Let's call it 4, -3. Alright, so there's a point at 4, -3, and somehow I'm supposed to come up with the values of the 6 trig functions of theta. So what do you think we should do first? Well, I think a picture is going to help. So I'm going to draw a Cartesian plane, and I'm going to draw the point 4, -3. Now that goes in a positive x direction and then a negative y, so it should be in quadrant 4. So there's my Cartesian plane. I've got a point at 4, -3. It wants trig values though, which is dealing with a right triangle. I don't see a right triangle. It even deals with an r, which is the radius of a circle. I don't see a circle. What on earth do I do? I think what I'm supposed to do is draw a ray from the origin out through that point. And I'm not sure what angle gave me this terminal side. Maybe it's this cute little negative angle, or maybe I was going in a positive direction and I went 50 revolutions around the circle and then stopped here. I don't know the angle, but this is a non-quadrantal angle. So what I'm going to do is find its reference angle and label it. The reference angle comes from the terminal side to the x-axis. Bam! That could be -25 degrees. That could be 332 degrees. Doesn't matter. It has that reference angle. Now I need a triangle. So I think what I'll do is I'll drop that perpendicular. Maybe you want to call that raising a perpendicular. But I'm just going to draw the best I can a straight line that hits the x-axis at a right angle, or an angle that measures 90 degrees. Now I know the, I kind of want to call that the base. I know the base of this triangle, or the length of this side, is 4. The y value, or this height of the triangle, you may want to call it 3, but remember it's the y value. So this y value has a negative associated with it. So the y value here is -3. I still need to know the radius, though. So that's a circle. I don't think we need to draw a circle here, but maybe this first time just to help visualize. That the hypotenuse of this triangle is the radius of this circle in standard position. I think I'm going to use the old Pythagorean theorem to figure out the radius. It says the hypotenuse squared is equal to those other two side lengths squared and summed. Negative 3 squared becomes positive 9. 4 squared is 16. Those add nicely to 25, so r, or the radius, is 5. When you take the square root of 25, there's always that negative 5 you have to worry about. But the radius of a circle, no matter how you point it, we're going to think of it as a length and as a positive number. So this radius will always be positive, and in this situation, our radius is 5. With those three side lengths, I'm able to tell you the 6 trig functions of theta. Sine of this red angle is defined as the y value over the radius. Y over r. In this game, that's negative 3/5. Sine has a reciprocal function. It's defined as r over y. It's just going to be the reciprocal of this, negative 5/3. Cosine theta. Cosine theta, as we defined it right there, is x over r. Well, that's going to be 4 over 5. And secant, its reciprocal is then just 5/4. Tangent is defined as y over x. So we take the y value of negative 3, put it over the x value of 4, and cotangent is its reciprocal, x over y. All right. All right, let's do it again. So this one, I just gave you a point, and we had to kind of maybe get a picture and then figure out what's going on, like what's the r, what's the radius. So I didn't really give you all the information, but I gave you enough information. So let's do another problem where I give you enough information, but we may have to go off and find some stuff. Something like this. We're given that the terminal side of theta is in quadrant 4. So that's quadrant 4. And we know one more thing. We know one of the trig functions. Secant of theta is 4 over the square root of 7. So they gave me one of the answers, but I need the 5 others, and I happen to know that the terminal side is in quadrant 4. Pause, see if you can get the problem set up. I think a picture is going to help here. So I have a terminal side in quadrant 4. So that means I should draw the quadrants, so the Cartesian plane, and then I'm going to draw a ray pointing out into quadrant 4. Sounds easy enough. 1, 2, 3, 4. That terminal side will have a reference angle formed from the terminal side to the x-axis, so going up here. I could even draw a triangle. Well, I do have some values, so maybe I'll deal with that first. I know secant is defined as the radius over the x value. So the radius must be 4, and this x value must be the square root of 7, or some equal ratio. Let's just not do that. Okay, let's say that the radius is 4, and it stops right here maybe, and the x value is root 7, meaning from the origin to this spot on the x-axis, the side length here measures the root of 7. But there's this triangle, there's this y value that I need to find. So how can I find the side length of a right triangle? I think the Pythagorean theorem is going to help out again. It says that the hypotenuse squared is equal to the other two side lengths squared and summed. So the root of 7 squared plus y squared will equal the hypotenuse squared. This one's not as pretty as the previous one, but I can handle this. 4 squared is 16. The square root of 7 squared is just 7. Subtract that over. That's a pretty number. The square root of 9 is 3. So I know the y value is 3, or that length is 3. So can I put a 3 right here? I want to, but there's something not quite right about this, because the y value needs to be a negative if I'm going into quadrant 4. So the length of this side length of the triangle measures 3, but the y value is negative 3. Just like the previous example. That y value is below the x-axis, so therefore the y value has to be negative. The green value is positive because I am to the right of the y-axis. The radius is always positive. I have the information now, those 3 side lengths, so I'm able to tell you all 6 values of the trig functions. Sine of theta is defined as the y value over the radius. Cosecant I have memorized as the reciprocal of sine. So if I know sine, I just have to flip this over as negative 4/3. Secant was actually given to us as 4 over root 7. Ooh, but I'm not really happy with that. In this course, I'm going to ask you to rationalize all denominators. So I don't like this radical being in the denominator. And that's easy to quickly handle. I can multiply by that radical. If it's a binomial, like 5 minus root 7, you have to multiply by the conjugate top and bottom. But if it's a single radical like we have here, you just multiply by this very fancy form of 1, and it's going to change what this looks like. So I claim their secant wasn't good enough. Secant of theta is 4 root 7 over 7. Now when I go to reciprocate secant to get my cosine, I am not going to reciprocate this version. This will put a radical back down in the denominator that I would have to rationalize. I don't want to do that. I think I'll just take this form, 4 over root 7, reciprocate it to get root 7 over 4. Or I could use the definition. Cosine is defined as the x value over the y value. So that's the root of 7, over the r value. So that's the x value over the radius 4. All right. Tangent is defined as y over x. So we have negative 3 over root 7. Again, we need to rationalize. Pretty simple. Negative 3 root 7 over 7. Cotangent, by definition, is x over y, or just the reciprocal of this, negative root 7 over 3. These are the values of the 6 trig functions of theta. So I'm just making you use these definitions over and over again, and I'm giving you enough information that you may need to go off and figure out some more. So pictures for sure will help. Pictures for sure help with the negativity, and then it helps you build the triangle so you can maybe find that third missing side link. Let's do another example. Same problem. I'm going to find the 6 trig values of theta. This time we are given, let me be as cryptic as possible. Let's do another secant where I give you it. Secant is 3. And we happen to know that sine of theta is less than 0. All right. We were given one of the answers, which I think I could reciprocate to get cosine. So I have 2 of the 6 values. But to find the other 4, the only information they gave us was that sine is negative or sine is below 0. It's interesting. Well, there's a mnemonic device that a lot of pre-calculus students learn called All Students Take Calculus. Now's a good time to maybe introduce that to you. I'm drawing a little Cartesian plane, and then it's all students take calculus. Next semester, take me. All right, all students take calculus. And what this mnemonic device helps us is it helps us kind of remember where trig functions are positive. So in red, I'm going to write the words that this kind of means. It's, again, all. So all trig functions are positive in quadrant 1. My radius is always positive. My x values are positive, and my y values are positive. Everything, or all trig functions, are positive in quadrant 1. In quadrant 2, sine is positive. Meaning, my x values are negative. So if you look at the definitions above me, anything with an x would be negative. Only sine and its reciprocal don't talk about x. They're just defined as the radius, which is always positive, and the y value. And the y value will be positive here in quadrant 2. T for tangent. Tangent is positive in quadrant 3, and cosine is positive in quadrant 4. So again, it's very quick. If you just tell me, oh, sine is negative, then one way to think about that is with this all students take calculus. I know that sine is going to be positive where everything is and where sine is positive. So for sine to be negative, I must not be in quadrant 1 or 2. I must be down here in quadrant 3 or in quadrant 4. I'm going to circle this in green, and I'm going to say The fact that it's negative means it's not in those two quadrants. I'd like to draw a ray from the origin out into space, and this tells me, well, don't do it in quadrant 1 and don't do it in quadrant 2. But it doesn't tell me if I'm in quadrant 3 or 4, so maybe this will. Secant is defined as the reciprocal of cosine, so instead of x over r, it's r over x. Now to get 3, I guess you could do like 6 divided by 2, but I bet the easiest thing would just be to let the radius be 3 and the x value be 1. 3 divided by 1 is this fraction that when I do the division, it gives me 3. Now for secant to be positive 3, secant is the reciprocal of cosine. So it is positive down here in quadrant 4. Basically, cosine is positive in quadrant 1 and 4. But we've already said it can't be quadrant 1. So I'm going to circle this in purple and say this tells us it can't be here in quadrant 2, nor can it be here in quadrant 3. So the purple and the green, these two statements, kind of clue us in that we must be in quadrant 4 yet again. I think all of my examples have been down here in quadrant 4. Okay, so when I start to talk about this information, I think I'd like to start by drawing a ray pointing in quadrant 4. I've said the radius is 3, the x value, a good one would be 1. Draw a right triangle. I need to know the y value. Again, the y value is below the x-axis, so the Pythagorean theorem better spit out a negative value. Let's go find it. X squared plus y squared will give me this radius squared. I know what x is. I know what the radius is. Subtract that over. Y squared is 8. I need to take the square root of both sides. So y is the square root of 8. That can be simplified. That's 4 times 2 in there. The square root of 4 times the square root of 2 gives me 8. And I happen to know that the square root of 4 is 2. So I'm going to call that 2 root 2. Oh, but let's not forget, when you take the square root of a number, there's a positive and a negative possibility. And because we're talking about this negative y value, I think I'm going to go ahead and label this as negative 2 root 2. All right. I think I have enough information. Oh, I should label my reference angle, theta. If secant of theta is 3, then cosine of theta is 1/3. 1 over 3. X over r. Sine of theta is defined as the y value over the radius. Cosecant is the reciprocal. Probably be smart to use that. I'm not sure. I'm going to flip this over. 3 over 2 root 2. Now that has a radical in the denominator, so I'd like to clean that up. I don't have to multiply by 2 root 2. I just need the radical to go away. So I'm simply going to multiply top and bottom by root 2. This will give me 3 root 2 over 4. Root 2 times root 2 is 2. That 2 times that 2 is 4. Tangent. Tangent is defined as the y value over the x value. Oh, I don't even need that over 1. It's just going to be negative 2 root 2. Cotangent is the reciprocal. Negative 1 over 2 root 2. Let's rationalize that real quick. cotangent of this reference angle theta would be negative root 2 over 4. All right. So those are the definitions of the 6 trig functions. They use x's and y's and r's. So we're talking about circles and triangles in standard position on the Cartesian plane. Go do your homework. See if you can figure out the 6 trig functions with the little pieces of information that I give you.